Uh, so suppose you study variation of this action where you have a matter coupled to gravity, and then what you find is that the gravity part of the action would give you the Einstein tensor, uh, and then you have a variation of the matter action, and you are going to set all, this entire piece equal to zero. Okay, and that is the new equation of motion that you will get. Okay, and we would recover Einstein equation if this variation of the matter action is proportional to the matter energy momentum tensor. Okay, so so one has to, of course, justify this identification, and we will not give complete justification to this story, but at least one can do some checks on it. First thing is that like T alpha beta typically is derived using the Noether theorem. The Noether theorem tells you that you make arbitrary variation, symmetry transformation, make that symmetry transformation local, find out what is the conserved current, and that conserved current is obtained by varying the Lagrangian and subtracting and multiplying it by variation minus the original Lagrangian, trying to ask what is the difference between these quantities, and that is a conserved quantity. Okay, typically this procedure does not give you a symmetric tensor, which is what you would require, uh, and the process that we will use here to write down the matter energy momentum tensor bypasses the Noether procedure completely, but it gives you manifestly symmetric tensor. Okay, so so in fact one can show that the T alpha beta that you obtain using Noether procedure and the T alpha beta that we have obtained by varying the action with respect to metric are essentially equivalent. Okay. In other words, all you need to do is to add a total derivative term of an antisymmetric tensor so that you can show that this symmetric matrix is related to the non-symmetric matrix that you derived through Noether theorem. Okay, fine. So now we can ask a question. As I said, I am not going to give a complete justification as to why this is called T alpha beta, but at one point one could just sit down and compute the T alpha beta from the Noether theorem, compute T alpha beta using this, and show that the difference between those two Noether those two tensors is a total derivative. Okay. Yes.
This we are taking as a definition.
This we are going to use as a definition. Yeah.
So usually introducing extra degree of freedom and taking the variation of the action with respect to those. For example, sometimes you use E, small
What
E.
What is E?
It's called Einstein, I guess.
No. Okay, continue.
So is it like that? Because
what is like that?
To demand that the variation with respect to that will give us energy momentum tensor.
No, Einstein has nothing to do with this. I mean, that is a different thing. That is trying to study the variation of a point charge, or not point charge, point particle. You look at a path of the point particle and you study the variation of the path of the point particle. That's not what we are doing, right? We are studying the variation of the field theoretic action, classical field theory. Now, Einstein is defined for the point particle, so it's a classical mechanics. Okay. Whereas what we are doing is classical field theory. Okay.
Okay. So
yeah.
I mean, we have geodesic equation for a free particle.
That's right. Yeah.
What happens when we have matter as well? I mean, how does a particle move under gravity? That is captured by Einstein's equation.
That is right. But geodesic equation is an equation defined with respect to a defined metric, right? So if you have if you have a space-time and in that you have some matter, then that matter defines the metric for you. In classical field theory,
Yes.
Einstein's solution to Einstein's equation, what is given by some g alpha beta, and what g alpha beta you would have is determined by what matter you have. Okay, you may have
Okay.
only a point like matter, or you may have a gas of matter, or stuff like that. Okay, once you put in that on this side, you get a specific g alpha beta. Now, for that, in that g alpha beta, if you want to move, look at the motion of a test particle, that g alpha beta is determined by the matter. But after that, the matter has nothing more to do.
So we can just take the metric from the Einstein equation and just use geodesic equation.
Exactly. Yes.
Okay.
So
Okay.
it is like asking a question about what would a probe see. Okay. So you have generated some background, like just to consider the electromagnetism. This thing, you have some charge distribution. That charge distribution has created some electric field. Okay. Now you want to move a test particle with some small electric charge, and you follow the trajectory of the test particle to determine what is the electric field, and by looking at the trajectory of this particle, right? Fine. So that test particle is not going to affect the electric field, and all the charge distribution that you have in the background, that charge distribution is giving rise to the electric field anyway. So you don't even look at the charge distribution also. Which, as far as the test particle is concerned, it only looks at how the total electric field distribution is, right? Exactly same way here. You have matter distribution in the space that produces some metric. Now you send a test particle and you want to see how the test particle goes, and from that you deduce uh, uh, whatever metric of the space time or whatever. Okay. Or if you
Okay.
have
So
the metric of the space time, you deduce the trajectory of the particle. Either way. Okay. So this has a tacit assumption that the particle on the geodesic is not affecting the geometry. That may not be correct, in the sense you may be actually following, thinking of a black hole as a object which is moving in space. And if you are trying to follow its trajectory, it is of course going to deform the geometry locally as it moves. Okay. So those are more complicated cases in which you need to kind of study uh, the time dependent geometry, because the heavy object is actually moving. Okay.
this right hand side, this captures the entire universe, right?
Yes. I mean, right hand side means this entire this thing, right?
Yeah.
Yeah.
Energy momentum tensor.
Einstein equation is supposed to explain. Yeah, exactly. The entire stuff. This is a matter energy momentum tensor, and this is the Einstein tensor. Okay. You can call that as a gravity energy momentum tensor. So what you're essentially saying is that the total energy with respect to this equation, it says that total energy of the universe is zero. Okay, positive energy inside the matter, negative energy inside the inside gravity. Okay,
Okay, sir.
so after all, this is just delta g alpha beta of S gravity, right? So you can just use this uh, definition to write that expression. Okay,
Okay, sir.
fine. So so we can now ask a question that, given this equation of motion for gravity, which we derived from one particular action principle, you could ask a question: is this action principle unique? Okay, or we could, or equivalently, we could ask a question that, can we add more terms to Einstein-Hilbert action and still derive the equation like this, or maybe small modifications of the equation which are consistent with non-relativistic limit. Okay. Now, before I kind of go ahead, I should put a small rider out here. This kind of question you could have asked even in ordinary field theory, classical or quantum, and that you derive say Klein-Gordon equation from classical field or quantum field, that quantum field theory action. And after you derive the equation, you could ask a question that is this equation coming from the action that we have used? Is that action unique? And answer is actually no. Okay, you can write down infinite number of different kinds of action which will give you the same equation. Okay, so this reverse process is never kind of unique. You can always write down additional terms in the action which are quantities that are proportional to the equation of motion, and they would just not contribute, and you'll recover the same equation of motion again. Okay, so that kind of yes.
Are the additional terms, I mean, can they be of forms other than del alpha phi? I mean, a total derivative.
Other than del alpha phi?
I mean, can the additional terms be something different than a total derivative?
No, no, no. I mean, see, total derivative is only one part of the Klein-Gordon equation, right?
Yeah.
You can also have m squared, phi squared term, and you could also have phi cube or phi fourth kind of interaction terms and so on. You know, what I'm saying is that you suppose you have a complicated equation of motion. Box phi is equal to m squared, box phi plus m squared phi is equal to some quantity which is proportional, some number times phi cube plus some number times phi to the 4 kind of stuff. Okay, some equation of motion. You can ask a question that is there any action principle which will allow me to write down this equation as through the variational principle? And the answer is typically yes. Okay. Now you can ask a question, is that action unique? The answer is no. Okay. You can always write down terms which are, when you do a variation, which are total derivative terms. Okay. And such total derivative terms do not affect equation of motion, exactly the way we saw that delta r alpha beta did not actually affect the equation of motion. Right. So those terms that we are talking about, of course, have to have derivative pieces to be able to give you terms such that the variation is total derivative. And it may even have other terms which are just proportional to equation of motion, but non-derivative pieces like m squared phi, or term proportional to phi cube and so on. Okay, as long as that expression is proportional to equation of motion, then you can get an equation like this, that uh, the original action gives you equation of motion. Let's call that equation of motion, say capital A. Then you get original action gives you capital A, and then all additional terms in the action gives you some alpha times capital A, or plus say beta times some total derivative term. Okay. Now, if you get some term which is like alpha times capital A, then your equation of motion is 1 plus alpha times capital A. And if alpha is say positive, then 1 plus alpha is never going to be 0, and therefore capital A is 0, and you still get the same equation of motion. So you could have additional quantities which actually do not change your equation of motion. Okay, and that non-uniqueness of the classical field theory action is always there. Okay, so we are not talking about that kind of class of terms, but we are talking about the class of terms which could uh, give low energy physics to be same. Like by low energy, I mean non-relativistic physics to be same, but the full relativistic action could be different. Okay. So, yeah, yes. Okay. So the first term that we could add is by holding the equivalence principle without violating equivalence principle is a term like this, which involves no derivative. Okay. Now, these kind of terms we could have just added simply because this is general coordinate invariant piece, and initially Einstein did not use that term. Later on, he realized that he could have added a term like that. Then he regretted adding that term. There's a long history about this. This term is called cosmological constant term. Okay, and as you can see that this constant is inversely proportional to the volume of space-time. Integral d for x root g actually gives you the volume of space-time, and therefore lambda is inversely proportional to volume of space-time. That means the in terms of dimensions, lambda has a dimension of energy to the 4, okay, or length to the -4 in the natural unit, both the things are same. If you do that, then just you add this term to the action and do the variation, you get the equation of motion with new term out here. Okay, and this new term is the cosmological constant term, which should give various interesting solutions. Okay, but first important thing that you then realize that if you are looking at Einstein equation for a vacuum configuration, that means you set the right hand side to be equal to 0, then the new Einstein equation in the presence of cosmological constant is r alpha beta minus half g alpha beta, r is equal to minus lambda times g alpha beta. So all you have done is that you have replaced this matter energy momentum tensor by a new object, which you call, which is effectively a new energy momentum tensor. And that new energy momentum tensor tells you that you can interpret lambda as vacuum energy. Okay, why vacuum energy? Because there is no matter, you are in vacuum, but still you have some non-zero energy, positive or negative, depending upon whether lambda is positive or negative, this thing. But but since this energy belongs to the vacuum configuration, you actually call it vacuum energy. Okay, so there is this notation also. For quite some time, people call cosmological constant as vacuum energy density, even now, in fact. Okay, fine. So now, since Einstein, so this is a little bit of history. Since Einstein realized that he could have introduced a term like this, and after all, he wanted to write terms up to 2 derivatives of the metric. This involves no derivative and therefore should have been there. He also, of course, introduced this term because there was observation by Hubble, which are not really, that there was a solution obtained to his equation, which showed that the universe would be expanding, and he did not believe that was the right thing, and therefore he added this term and tried to show that the universe would be static, and then he wanted to kind of get some natural principle which would explain why a term of this kind should or should not be there. Later on, it was discovered that the universe is actually expanding, and then he wanted to set lambda to 0. And there is no principle which allows you to do that, in fact. Okay, well, there is, but that came up much later. This thing. So a generation or two of theoretical physicists kind of spend their time finding ways of kind of arguing as to why this term shouldn't exist, and with, of course, no success. There is one beautiful proposal which would have set this quantity to 0, which is what is called supersymmetry, which naturally tells you why lambda would be 0. But we know that that there is no supersymmetry in nature, and if the supersymmetry is not there in the nature, then and if you assume that actually the original theory was supersymmetric, but the nature chose not to have supersymmetry, then supersymmetry naturally tells you that lambda should be non-zero. But the observed value of lambda, of course, after all these efforts, it turned out that the cosmological constant is actually non-zero, and not only it is non-zero, it is positive, which is a bit of a kind of difficult scenario to handle. And in addition to that, the non-zero value is very, very small. Okay, and so now I should mention one thing, that like when one says very small, it's a very relative statement, and I can tell you why this small is not really small, but it's actually quite large in a different sense. But before that, let me just complete the argument that it was, after having obtained this quantity to be non-zero, it would naturally seem that, like, maybe, quote unquote, ultimate action that you would write down may be supersymmetric, and it would because the supersymmetry is broken, spontaneously by the vacuum or by nature, it would naturally explain why lambda is positive. Okay, because supersymmetry tells you that if it is broken, the lambda would be actually positive. Okay, now with all that, it seems like that would have been the best way of solving the problem, but that is not true because the scale of supersymmetry breaking from experiment seems to be reasonably large, and you would have expected lambda to be of the order of something like 10 to the minus uh, 20 times the Planck mass to the fourth. Remember, it has the energy scale of Planck mass energy to the 4, so mass to the 4. So it should be something of the order of 10 to the minus 20 times Planck mass to the 4, whereas it is of the order of 10 to the minus 70 times Planck mass to the 4, and 5 6 uh, I mean 10 to the 50 50 orders of magnitude difference between these quantities do not have a natural explanation in terms of breaking of some non-existent non-observed symmetry and stuff like that. Okay, so when I say that this quantity is very small, I mean that with respect to Planck mass to the 4, a number multiplying Planck mass to the 4 for you to get this uh, observed value of lambda is something of the order of 10 to the minus 70. Okay. I mean, I think it is 10 to the minus 67 or something, but let's not worry about that detail. Something of the order of 10 to the minus 70. Okay. On the other hand, if you want to ask this question, if you want to step back and say that, like, okay, I have this thing. Suppose I know that there is matter in the universe. I write down a matter energy momentum tensor and the cosmological constant contribution to the energy momentum tensor. I treat that whole energy momentum tensor to be the total energy momentum tensor on the right hand side. This thing, I take g alpha beta, lambda g alpha beta on the right hand side, and then I ask a question that among this total energy momentum tensor, what is the contribution of the cosmological constant versus what is the contribution of the matter? Okay, so and the role reverse is totally there because the total contribution of the cosmological constant to the energy density of the universe is close to 70%. Okay, so almost 70% of total energy density is sitting inside the cosmological constant, and only the 5%, only 5% of the total energy density of the universe is something that you actually see. Okay, remaining 25% is not visible. We do not know what it is, and we have coined a very nice name for it. We call it dark matter. Okay, so that is what is called a dark matter. Cosmological constant energy density contributed by cosmological constant is also referred to as dark energy. So dark energy plus dark matter contribution to the total energy momentum tensor of the universe is 95% actually, and what you actually see is just about 5%. Okay, so that is the thing. So therefore, in spite of numerically having a small value with respect to Planck mass, in reality, the contribution of cosmological constant to the energy total energy momentum tensor is significant, much bigger actually. Okay. In other words, it also tells you that the matter energy momentum tensor is very small. It is of the order of it is roughly of the same order, like 10 to the minus 70, 71 times Planck mass to the 4. It just tells you that the matter is spread out so sparsely in the universe that there is large amount of empty space. Okay, of course, one is talking about the energy density. Some regions may have very large energy density, like in the neighborhood of black hole or some such thing, but that's not what we are computing. We are kind of computing average values. Okay. So this is an enigmatic quantity that was put into the Einstein-Hilbert action, and now of course we see that it is an important quantity for us to understand. Okay, and in realistic terms, we really do not understand what that object is. Okay, I mean, you put a term of that kind in the action, but we don't know what it really means. Okay, fine. Now, if you say that, like, okay, I don't want to kind of stick to equivalence principle in a very strict sense. I may allow some weak violation of the equivalence principle. Then you can in fact add infinite number of terms to the action. Okay, and there are some of those are written out here. You can have a Ricci scalar squared term, or Ricci tensor squared term, or Riemann tensor squared term, or derivatives of some of these guys. This thing, as long as you construct a scalar out of it, you can write down whatever you want. It doesn't have to be quadratic. It can be cubic, quartic, any arbitrary power. Okay. In fact, um, people have written down actions which are inverse power of the Ricci tensor also. Okay. So and stuff like that. Of course, there is nothing. Nobody stops you from writing whatever you want. Uh, you know, it has only utility if it has any potential to explain something that is puzzling in the theory of gravity. Okay. Otherwise, if you write down 1/r action, you can freely write it. If it cannot explain anything, then it just goes into the dustbin. Okay. Fine. So, so of course, these kind of terms, they not only violate equivalence principle, they could in fact potentially modify the non-relativistic limit. Okay. So, in order to not have violation of non-relativistic limit, we will have to put constraints on this A1, A2, A3, A4 coefficient. In other words, you are doing an experiment, and that experiment tells you certain quantities related to curvature of space-time, or uh, whatever experiment you do, like a deviation from the solution to Einstein equation and stuff like that, using say torsional pendulum stuff, whether gold versus say lead have different gravitational pull on objects and stuff like that. If any of those things are going to kind of give you a non-trivial result, they will tell you what these numbers are. If they give null result, then they will constrain these numbers. They will say that A1 cannot be larger than certain number. That number depends on the accuracy of the experiment that is performed. Okay, so what we will find is that consistency with the non-relativistic experiments would put constraints on this coefficient AI. Now, coefficient AIs are typically dimensionful. Okay. Now, in this particular case, the ones which I have written down, A1, A2, A3, are not dimensionful simply because the Riemann tensor has dimension 2. So Riemann square has dimension 4. Okay, so integral d4x root g r squared is actually dimensionless, and therefore A1, A2, A3 actually wouldn't have dimensions, but A4 would. Okay, so generically, AIs that you would write down would be typically dimensionful, and therefore, if they are if you want to put them to be non-zero, then those quantities should be small for them to be consistent with the experimental constant that we have. Okay. Now, I should mention one thing, that the experiments that we have done to measure deviation from Einstein's theory are not done very extensively, in the sense that, like, those measurements can be done, have been done, say, for deviation in law of gravitation over the distance scales of, say, few millimeters to a few kilometers, and then distance scales which are like cosmological distance scales, like parsec to several megaparsec kind of thing. Okay, but what about what happens to this thing between say, few kilometers to a parsec, or what happens to the law from few millimeters or few micrometers down to, say, angstroms and fermis and smaller and smaller length scale? Is there any deviation? These kind of experiments are still open, and one doesn't know what kind of constant they would give. Okay, by that I really mean that that the gravitational force could still go as 1/r squared, indicating that gravity is the elementary particle associated with gravity is still massless. But in addition to that, you may have one more force. So right now we are talking about four forces: strong, weak, electromagnetic, and gravity. But you may have a fifth force, which may have a range which is, you know, say uh, smaller than say an angstrom, or maybe larger than few kilometers, but smaller than few uh, parsecs. You know, and uh, those kind of arenas still open. Of course, they are. I mean, experimentalists are still bridging those gaps by doing, uh, large distance scale experiments and so on. Okay, fine. Now, besides writing terms of this kind, you could write down some another set of models which are called scalar tensor theories of gravity. Okay, the scalar tensor theories of gravity have, besides G alpha beta, another fundamental scalar called phi, and you write down the action involving both G alpha beta and phi. But why is this a scalar tensor theory of gravity? Because not only G alpha beta, but phi also couples universally to matter. Okay, so phi is not like matter, in the sense that like phi couples to gravity, and phi couples to maybe some other fields. It's not like that. The way G couples universally to all matter, phi also couples universally to all matter. Okay, so therefore, if you want to do a fifth force experiment, one of the candidates is this scalar field that you could be looking for. That if you find additional a deviation from say Einstein's theory, then you could ask whether that deviation could be fitted by a scalar, a force generated by a scalar field. Okay, uh, so far it has been negative. Okay, fine. So let's first look at the vacuum action of the scalar tensor theory, and that action is typically written like this. Okay, so you have S integral d4x root g, which is a common volume element, and then you have some function of phi multiplying the Ricci scalar plus the kinetic term of phi, okay, minus v of phi, okay, and uh, clearly you can see that it is not a single theory, because depending upon what is the function that you choose here and what is the potential that you choose here, you have different theories. Okay, so uh, so you make a pick of this function, you get one theory. So some other thing, you get another theory, and each one of these functions would have a different proposal to make. It will have different experimental signatures, and therefore this is not a single theory, but it's a class of theories. Okay, so therefore one calls it scalar tensor theories of gravity. It's not a single object. Okay, but there is something interesting that you can see here, and that is that if the scalar field takes a fixed value, say constant value all over the universe, say all over the space, then that constant value would give you a constant value here, because v of phi is just some function of phi. Okay, and if phi takes some value phi naught, then v of phi naught is typically some number, because phi naught is a number, and v of phi is just a polynomial function of phi, right? But if you have that, then that number times root g times d4x is precisely the cosmological constant type of action. Like that. Okay. So therefore, you could say that the scalar tensor theory, okay, could naturally tell you that cosmological constant is actually a dynamical object. Okay, it's not a constant it's not a constant piece in the action, but it is supposed to be the value of the potential for a constant configuration of, say, a scalar field in this particular case. Okay, so this kind of explanation of cosmological origin of cosmological constant is a little more satisfying, in the sense that like these kind of situations have been studied in physics in various other contexts. For example, in case of superconductivity, you find that the potential has non-zero value, and as soon as phi takes non-zero value, that is the one which kind of generates a supersymmetric state in a particular system. So not supersymmetric, superconducting state in the system. Okay. Similarly, you could kind of study spontaneous symmetry breaking in quantum field theory. For example, many of these meson particles that you have to observe in particle physics experiments are actually effects of some continuous symmetry spontaneously broken, and we have actually observed them experimentally. Okay, so seeing something like that is I mean, is nothing new, because we have already seen that this kind of stuff in various other systems. So if cosmological constant is just a term of this kind, it would have a little better stature than just adding a root g times lambda term. Okay.
So
Yes.
isn't this sort of an action what we write for something like inflation?
This kind of action? No. The action that we write for inflation is this term, but the r is as it is. There is nothing couples to r here.
Yeah, F is 1.
F is 1. Yes. Yeah. That is right. But like, in scalar tensor theory of gravity, what you have is that, like, if you couple matter, then this scalar couples exactly the same way the G alpha beta would couple. So it will couple to all matters exactly in the same fashion. Okay. In the case of inflation, it is not like that. In the case of inflation, you say that there is an additional scalar field which couples to gravity. Okay.
Yeah.
So slightly different. Okay. That additional scalar field may not couple to other matter. Okay. So yeah. So and the other thing that I wanted to mention was that this has another advantage, that whenever phi takes some fixed value in the vacuum, then not only you generate a cosmological constant piece, but f of phi also takes a fixed value, and that fixed value you could interpret as a Newton's constant. Okay. So this way of writing a particular theory gives you a formulation which contains no couplings. Okay, there are no couplings in this action. Okay, all the couplings that you see in Einstein theory are obtained by actually giving some background value to the scalar field. So scalar field takes phi is equal to phi 0 value. That tells you what is Newton's constant. That tells you what is cosmological constant. Okay, and in that sense, these kind of theories were quite appealing because they do not have any free parameter to tune. Okay, and in fact, when it's of course a belief, but like, Einstein thought that there must be some unified theory from which all these different forces could be derived, and there are, last about 70 years, we people working in high energy physics are basically trying to see whether actually something of that kind really exists, whether one can write down a grand unified theory, or they can write down a single theory from which all these theories could be derived. The problem seems to be harder nut to crack, but nevertheless, there have been several attempts of that kind. And one natural thing that you would think of, the theory from which all these four forces could be derived as some kind of different manifestations, would be to have least number of free parameters in that theory. Okay, so possibly only one coupling constant, or possibly only one parameter which defines the theory, and so on. If you have something like that, then and if that can predict several coupling constants of the four fundamental forces, that would be something very good, because it will have very large predictive power and therefore large falsifiability. You can do experiments and check whether this theory is actually going to make sense, and so on. Okay.
So but what you're saying, that it would be nice to have a theory that only has one free parameter.
Yeah.
That is not really in our hands, right? That is just how nature is. Like,
No.
it is will be actually more than one parameters.
Oh yeah, certainly. I'm not saying that. What I'm saying is that, like, I when I say one, I do not necessarily mean that like it has to be one. What I'm saying is that, like, you want to have a fundamental theory which has least number of assumptions. Okay, least number of tunable quantities. Right? If you write down a coupling, then that is a tunable object.
Yeah, I mean, in our hands it is, but like at least we would think that it is fixed and we need to determine it by some experiment.
Yeah, but actually, as you will study in quantum field theory, that the couplings are not fixed. You know, in fact, we will study in advanced atomic course also that the couplings are not fixed quantities. They depend on the energy scale at which you study the theory. So at high energies, the value of coupling could be one thing. At lower energy, value of the coupling could be totally different. Just to give one example, uh, electrodynamics, has the coupling E squared upon 4 pi, and this E squared upon 4 pi at atomic physics scale, that means of the order of few hundred electron volts to about a few kilo electron volts. In that, at that energy scale, this value E squared upon 4 pi is 1 over 137. Okay, but if you are doing an experiment at LHC, which is of the order of about 10 tera electron volts, okay, which is about like 6 to 7 orders of magnitude larger than the atomic energy scale, then E squared upon 4 pi is actually 1 over 128 or 129, I think. Okay, so this number has actually gone up from 1 over 137 to 1 over 129 as you scale the energy up. Okay, so you find that although the coupling written in the action is a number, the coupling that is there for the physical theory actually changes as a function of energy. Okay, so in that sense, they are actually functions of kinematical objects like momenta and energy and so on, and therefore there is a natural way to think of couplings as vacuum expectation values of some other objects. Uh, And in fact, like, I mean, I don't want to get into string theory kind of stuff, but like this, you may have heard of something called ADS-CFT correspondence, which is some relation which tells you how quantum theory of gravity in some space is related to another theory, which is a quantum field theory without gravity. So you can give a gravity description in one space by non-gravitational theory in some other space. And in this particular relation, all the coupling constants that occur in non-gravitational theory are actually vacuum expectation values of the objects which are in the gravitational theory, and therefore none of them are actually free parameters. They are all vacuum expectation values. Okay, so but this is not to say that like therefore it should occur like this all the time, but most of the people believe that this may be the best way of attempting uh, a most fundamental description of all these forces. Okay. Okay.
Yeah.
Oh, yeah. No, I just thought I may have lost all of you. Okay. Fine. So another thing that could happen is that the phi that you have chosen, like as I was saying that like phi could take a value phi equals phi 0, and in that case this quantity is a constant and this quantity is a constant. Okay, and you can call this quantity cosmological constant and this quantity Newton's constant, or inverse of the Newton's constant. Okay, but you may have a situation where phi itself could be evolving in time. So phi is equal to phi naught, but phi naught is a function of time. Okay, then if it is a function of time, then your cosmological constant itself is a function of time, and your Newton's constant could also be a function of time. Okay, so you could allow many more interesting scenarios in scalar tensor theory than say in Einstein theory, in which you have a fixed number sitting here and a fixed number sitting there. Okay, uh, having said all that, there has been no evidence of scalar tensor theory so far. Okay, so in spite of this being an interesting idea, the nature hasn't chosen to kind of follow this line. Okay. Okay. Now, besides the kind of actions that we wrote down, which all assume that the metric that we write down in these actions is compatible with connection. That means metric is covariantly constant. Okay, but you may generalize that. You may say that like, okay, I have a connection which is not symmetric in beta and gamma. That means you can decompose gamma alpha beta gamma into gamma alpha beta gamma symmetric plus gamma alpha beta gamma antisymmetric in beta gamma. Okay, and if you have that kind of stuff, then you could write down more general theories of gravity. The gamma and alpha with beta gamma antisymmetric is what's called a torsion, and you have torsionful gravity, and in that case you could ask what are the implications of those. Okay, again, as I said, that most of these modifications are very strongly constrained by experimental data. Okay, and in fact, if you attend any experimental relativity lecture where somebody is looking for fifth force or deviation from Einstein gravity and all, and parametric graphs are being drawn, you'll typically find that their graphs are drawn with Einstein gravity sitting at the origin of the graph, and then there are error bars or allowed regions in the parameter space, and you find that the Einstein gravity is typically sitting right in the middle of that allowed region. Okay, and the allowed region is shrinking day by day as they improve their experiments. So many such scalar tensor theories and torsion full connection theories and all are getting badly constrained. Okay, uh, it's also unfortunate that there is no deviation, because if there was a deviation, at least it would have given us some clue as to how we go about studying quantum theory of gravity, whether it requires some additional field, whether it necessarily requires some additional field or not, and stuff like that. There is hardly any guidance on this one. So we are kind of stuck both on the gravity side as well as on the particle physics side, because there is no guidance as to how you go away from standard model of particle physics either. Okay, fine. So now what we'll do is we'll switch to looking for solutions to Einstein equation. Okay, and so so to do that, we'll have to kind of uh, do some set up some formalism. So for some time we will actually not be looking at uh, solutions to Einstein equation, but we'll kind of do some setup which may be useful for looking for a class of solutions. Okay, so let's consider kind of go back to classical dynamics of a single non-relativistic particle, and this is kind of Newton's law that the acceleration of the particle is proportional to force. Okay, and force is of course gradient of the potential if you have kind of a system like this. Okay, and what you do is that you kind of decompose this second order equation into first order equation, or convert that into a matrix form, whatever you want to call it. Uh, and so what you do is that you said that m times dx by dt is p, and dp by dt is equal to minus dv by dx. Okay, so you can kind of say x and p forms a column vector, and you can convert this into a matrix equation. Okay, now to solve this particular problem, this is just the first order set of equations. So what we need to do is to give some initial values of xi's and pi's. Okay, and then just use these equations to evolve the values of xi's and pi's. Okay, because if you know what is the initial value of x and p, then you know what is p on this side anyway, and you know x, then you know what is dv by dx. Okay, so if you know this, then you know how p is going to evolve in time and x is going to evolve in time. So you determine values of p and x at next instant of time, plug them back on the right hand side, and derive it at the next instant. Okay, that is how the initial value problem is solved. Okay, so this is the statement. Given xi pi at time t, we can determine them at time t plus delta t using these equations. Okay, fine. So that is the way one would go about solving it. Okay. Now, to obtain a full solution, this procedure you have to iterate several times. You do this, then you get a new one at t plus delta t, do it again, and keep doing it. Okay, until you get a global solution. Okay, now let's try to do this for the Einstein equation. Okay, so how do we go about doing this kind of stuff for Einstein equation? Okay, so here's a equation. We already know this stuff. And if you go back to this equation, then what you find is that like what you are looking at is the time evolution of the initial data. Okay, so initial data is given at a fixed time, and then you evolve that in time, and you ask what happens to the next instant of time for the for a given initial data. Take the solution at next instant of time and treat that as an initial data and evolve it again. Okay, that is the process that we follow. Okay, when you look at Einstein equation, then that is completely in a covariant form. Okay, so we'll have to ask several questions to be able to do it in the initial value problem form. Okay, first thing is that we'll have to determine the time evolution uh, of the variables, and to do that you have to choose a notion of time. Okay, now you remember that like we are studying the theory with general coordinate invariance. Okay, so you write down the equations. You can do arbitrary coordinate transformation which are time dependent. It can be horribly space and time dependent, and what you would have called time in one coordinate system may not even look like a time in another coordinate system. It may look like some other object. Okay, so therefore there is no clear-cut notion of what you call time. Okay, but nevertheless, what you need to do is to choose, find ways of defining a notion of time. Once you define a notion of time, then with respect to that notion, you could define a space or a hypersurface in the space, okay, to which the unit vector of time is orthogonal. Okay, remember any surface is defined by a vector orthogonal to that. Okay, so if you are looking at a three-dimensional hypersurface in four-dimensional space, then the normal to that hypersurface, okay, is the vector which defines that hypersurface. What we want to do is to look at a hypersurface to which the arrow of time is orthogonal. Okay, fine. Now, clearly, if the surface is orthogonal to time direction, then that surface is typically called space-like surface. Okay, it's called hypersurface because surface is typically two-dimensional. We want to define a three-dimensional surface. That's a hypersurface. Okay, and what we want to do is to give initial data on this surface. What is the initial data? Now remember, this equation contains two derivatives of metric. Okay, both in R alpha beta as well as in R. Okay, so and you know that if you are solving a second order differential equation, then you need to give two initial conditions. Okay, and you could, if you are giving them as initial conditions, then typically you define, in this particular case we will give the value of g alpha beta and time derivative of g alpha beta. Why time derivative? Because we are evolving this equation in the time direction. Okay, so that is what we will do. Okay, we define g alpha beta on this space-like surface, and we define time derivative of g alpha beta on that space-like surface. Okay, so and this is what we will treat as initial data. Now, it is not necessary to use it in this fashion. You may want to solve a boundary value problem that you define a value of g alpha beta at two different locations. Okay, that is also good enough. Okay, but boundary value problems for the nonlinear equations may become quite complicated. Not that this initial value problem is very simple or something, but boundary value problem could be much more intricate. Okay, fine. Now, so let us try to understand what is it that we are trying to do. Okay, I mean, do we really need all that stuff as the initial data? Okay, so let's look at the Einstein tensor. Okay, which is R alpha beta minus half G alpha beta R, which we call capital G alpha beta. And we know that the Einstein tensor satisfies, oops, this is the reverse. Yeah, some small space was missing, and because of that, there's a problem. Yeah, it will correct it. Okay. So, so it satisfies the Bianchi identity, which is d alpha of g alpha beta equals 0. Okay, that is the equation. That's how it should look like. This thing. Uh, so, what we could do is that we could work. Yeah. Okay. So there it is. So what we could do is that we could work in some coordinate system in which gamma alpha beta is 0. Okay, gamma alpha beta gamma is 0. So the advantage of doing that is that we can convert this equation into a simpler form. Okay, convert all the covariant derivatives into partial derivatives. Okay, so if you do that, then this equation can be written as del 0 g 0 beta is equal to del I gi beta. Okay, that is what this equation would boil down to. Okay, fine. So here's a small exercise that what you need to show is you take d alpha of g alpha beta. Okay, this is the equation. And what you need to show is that this equation does not involve third time derivative. Okay, fine. So if this equation does not involve third time derivative, okay, then g alpha beta, okay, this would imply that g0 beta, okay, which is the quantity here, there's a derivative acting on that. But since d alpha g alpha beta equals 0 does not involve third time derivative, one time derivative is already here. So g0 beta does not involve second time derivative. Okay, so it does not involve two time derivatives at all. Okay, so therefore the the piece which you would have thought would have contained two time derivatives because g alpha beta involves two derivatives of the matrix actually does not contain that. Okay, so as a result, this equation, okay, does not evolve the initial data. Okay, because to evolve the initial data, you need second order equation because you have given the initial data corresponding to second order equation. Okay, fine. So what we need, so what we find is that the equation satisfied by G0 beta, which is G0 beta is equal to minus 8 pi Gn times T0 beta, okay, is actually a constraint on the evolution of initial data. Okay, so what you need to show is, I mean, you don't have to show, but like, once you show that this is true, then it naturally follows that this equation tells you that whatever is the value of T0 beta, okay, this has to be true at every time epoch. Okay, so this is a constraint that you have to kind of impose on the solutions. Okay, so once you have kind of converted this set of equations into constraints, then the actual evolution equations are only these. Okay, among these equations, remember the beta can take zero value. I mean, there is nothing which stops you from putting G00 to be equal to T00 quantity. Okay, but once you have gotten rid of those, I mean, gotten rid of in the sense you have converted them into constant equations, okay, which are true at all times. Okay, the evolution equations are only these. But Ij take only three values. Okay, they are spatial coordinates, and Gij is symmetric, so therefore there are only six equations. Okay, because it is 3 into 4 by 2. Okay, and only six equations. Whereas G alpha beta, small g alpha beta, we had like 10 non-trivial components. So we are again in a situation where we have six equations for 10 unknowns. Okay. So of course this gives rise to a fourfold ambiguity in determination of the solution because out of 10 unknowns in G alpha beta X, which is the metric tensor, only six of them could be determined from these equations of motion. Okay, but by now we know what is this. Okay, this fourfold ambiguity is just related to the statement that whatever solution you have got, you can always do a general coordinate transformation of that solution and you get a new solution. Those general coordinate transformations are generated by x mu going to x tilde mu, which is some functions of x mu. Okay, that this transformation was 4 functions, f mu of x, okay, and those 4 functions introduce the 4 parameter ambiguity in the solution, okay. So what one could do is to fix that ambiguity by choosing a specific gauge, okay. So one could choose a gauge so that
Sir,
yes,
sir, when we work in a frame in which Christopher symbols vanish,
yeah,
there should be six-fold ambiguity, right? Because we can also do rotations. Because if we are in a local frame,
yeah,
locally inertial frame, we can
yeah,
do Lorentz transformation and rotations.
yeah,
So there should be
yeah, but
six-fold degeneration.
no, but
I mean,
those
ambiguity.
transformations, no, those transformations do not change the metric at all, no,
Yes.
right? So that ambiguity is not a parametric ambiguity at all, right? So what we have is different. What we have is that we have 10 parameters and 6 equations, okay. The 6 parameters that you are talking about was the opposite problem, that G had 10 parameters and you had 16. I mean, G alpha beta had because of symmetry had only 10 components, and uh, x mu going to x tilde mu had 16 parameters. So you had 6 free parameters to kind of fix 10 parameters in the metric. And what we said was that we can choose a coordinate system by which you can set all those 10 parameters in the metric to be something proportional to, say, Minkowski metric. And then the remaining 6 actually leave the Minkowski metric invariant. Okay. So if you are doing Lorentz transformations or rotation, that would leave the metric invariant actually. Okay.
Okay. So that means they are not new solutions at all.
They are not new solutions at all. Yeah.
Yeah.
Okay.
Okay.
Yeah. In fact, these are also not new solutions. That this 4 parameter ambiguity, because they are general coordinate transformations. Okay. And what we are going to say is that the one solution and its general coordinate transform solution are physically no new solution. That is what we want to argue. Okay. Right. In other words, we want
Okay,
to
sir.
say, in other words, we want to say that general coordinate transformation is like a gauge symmetry. Exactly like in electrodynamics, mu going to mu minus del mu of lambda does not change the electric and magnetic field. Okay. Similarly, G mu nu going to G mu nu tilde, which is a tensor transformation of G mu nu, okay, does not generate any new geometry. It's the same geometry written in different set of coordinates. Okay. So of course, this fourfold ambiguity can be kind of fixed by just making a choice of gauge. Okay. Exactly the way we make a choice of gauge in electrodynamics, here also we'll make a choice of gauge such that we get a solution in a particular choice of gauge. Okay. So so maybe I can stop at this point and we can kind of do this gauge fixing next time. Okay. Is that okay? Are there any questions?
I have a question with
Yeah.
Levi-Civita
Tensor.
tensor density.
Okay.
So when we transform it using general coordinate transformation, it takes
Yeah.
4 partial derivative terms. I mean,
Yeah.
del x
Yeah.
prime by del x. Yeah.
That's right. That's yeah.
So how come it has a weight of -1? Tensor
It is a,
density has a weight.
yeah.
Weinberg
Yeah.
says that it has weight -1, but I can't understand that.
Oh, it has a weight -1 because as a density, no. See, it is not it's not a tensor. It has a density factor. That means you get a determinant of del x by del x prime, right? Under transformation of tensors, you don't get determinants. You get del x by del x prime to some power. Okay. Here you have antisymmetrized fourth power. Okay, so that is like a determinant of that quantity, right?
There are 4 terms,
Okay.
so
Yeah, but
yeah, that
all four terms have different index, no?
yes.
Now, if you remember, if you look at determinant, then determinant always has the product of, you know, uh, one element to with respect to product of say different elements, and those different elements have different row and column entries. Okay, like take 2 by 2 matrix. You know, 1 component multiplies 2 component, and 1 component multiplies 2 component. So you can see that the row index is not repeated, no, nor is column index repeated in the product quantity, right? So you can write down this as a product of epsilon tensors. Okay. So what he says that it is a density of weight minus 1 is with respect to what is the power of the determinant that occurs in the transformation property. Okay. So although it is a fourth power of del x by del x prime, it is actually only one power of the determinant. And that's what he's talking about.
Okay.
Okay. So it's an issue
It's
of
basically the definition of how we take determinant.
that is right. So it is a difference between a tensor and a tensor density actually. You know?
Yeah.
So because of the tensor density, you get determinant sitting around. Tensor doesn't have a determinant sitting around. Okay, so tensors have rank, densities have weights. That is the difference.
Also, sir, can you give a problem in which boundary terms are important? I mean, they do not vanish. Action does not vanish.
Good question. I can try. Yeah, I can
Even
try to do
this
that.
action that we have written, the boundary term don't trivially vanish.
Which action?
The Einstein-Hilbert action, as it
Yes,
is, the del nu g terms don't vanish unless you demand that they are also zero at the boundary.
exactly. So that is what we discussed in the beginning. And but the thing is that, like, you know, you may have variation non-vanishing at the boundary. In that case, you need to add a new term so that the variational principle is well behaved. Okay. And one of the kind of popular such boundary term is called Gibbons-Hawking term. Okay. But there are, like, you know, if you do different kinds of theories, like, you know, if you work in anti-de Sitter space, then there are some things called Balasubramanian cross terms, okay, which are different kind of terms that you could introduce. And yeah, so that your variation principle is well behaved. But
Also,
yes,
sir,
yes,
uh, like when integrating, well, usually in the action we just integrate space and time from minus infinity to infinity.
yes.
Like, should we really refer to these so-called infinity points as some boundary?
Well, uh, it's a question of, you know, how do the fields behave, right?
Yeah, and
So
like in our case, we don't have
yeah,
any sort of visible boundary, right, for the universe.
well, we don't know really.
Yeah, I mean,
It could even be compact. You know, one doesn't know really.
yeah, like we don't have any knowledge of how fields are at the
Yes,
edge, whatever.
yes, we don't know. True.
So, like, I mean, mathematically, we just impose that fields vanish at infinity, like
Yes,
in entirety of quantum field theories and all, to get
exactly.
normalized results.
Yes.
But like
Yeah.
whether
So
that we should be doing, I'm not sure.
yeah. It is true. One doesn't know all this thing. But, like, you know, in quantum field theory, it is a little different thing. In quantum field theory, even if the particles are like, you know, you know few feet away, you could say that, like, they are at infinite distance away. You know, in some sense, right? And therefore, you could say that, like, the field has vanished. In quantum field theory, also, you make a very specific assumption, saying that, like, you know, you define in states at far past at and far separated states, and then you evolve them in time, bring them closer, and then at some finite time t, or let's call it minus t, at finite time minus capital T, the interaction is turned on. Okay, and then these particles actually interact, and then at some finite time plus t prime, okay, the interaction is turned off and the particle just evolve. Okay, this is a very specific assumption that one makes in quantum field theory for all the calculations. You know, in reality, of course, that is not the way it is. The interaction is always on. Okay, but this is one way of kind of defining how you would do the computation. Then, of course, at the end of the computation, you relax the way you have done the computation, but it does, of course, carry some kind of remnant information about this. Okay.
Yeah.
So yeah, here also what one is trying to say is that, like, that, let's suppose you are studying black hole, then you say that, like, black hole is a solution such that if you go reasonably far away, you recover Minkowski space. Now, we don't really know whether that is true. It may you may actually recover some de Sitter space, or you may recover anti-de Sitter space, or you may recover some weird other geometries, some Taubner space. One doesn't know, right? Uh, so there are, like, certain class of assumptions that you say that, like, asymptotic geometry is something like this in Minkowski space, or whatever, and then you actually look for a solution.
Okay.
Any other question?